So here's our new updated compound interest formula. Instead of what we had before, I'll just remind you, before it was A equal to P times 1 plus R to the teeth power. Now we've got an extra piece in there, that N, which is the number of times you're compounding it per year. Let's actually point that out first. N is the number of times interest is compounded per year. And it is at regular intervals, right? Meaning if I say we're going to compound interest 3 times per year, we don't do it like the first 3 months and then not the next 9 months, right? If we were doing it 3 times per year, we do it once every 4 months, right? So it's an equal interval every time. As before, the A here is still the amount of money we're going to have at time T. P is still the principal, which is the amount we're starting with. R is still the interest rate as a decimal. And T is still the time in years. And I do want to mention, because it is going to come up a little bit, there is an alternate way of writing this formula that we don't usually do, but I just want to use one of the rules of exponents to show you something slightly different. So I'm going to rewrite this as P times 1 plus R over N to the N to the T. That's totally okay, right? When you have a power to a power, you would multiply the powers. So this and this are definitely the same. You know, a little lag on my camera here. Interesting. Anyway, so just we don't usually write it this way, but I'm going to use it like one time when I show you something. So just be aware that this and this are totally the same. Let's calculate some stuff. Also, for those of you on Zoom, you're welcome to ask questions via chat as usual. Yeah, let's look at an example. If you look at these, so we have $1,000 to invest. You plan on investing it for 10 years, and you have 2 choices for accounts. One that pays 6% simple annual interest, or the other paying 6% interest compounded monthly. Which one should we choose? And obviously, the goal is to make more money. So we're going to choose the one where we get more money. Let's do them both. So we're going to calculate it using the simple interest formula. And again, right, I'm really just taking my formula and throwing everything into it. So I know that for the simple interest, A equals P times 1 plus R to the teeth power. In this case, I feel like I'm saying teeth like when I say the teeth power, like it's like the things you eat things with. Obviously, that's not what I'm saying, but you know, it sounds kind of funny. You know, like, oh, the teeth power. Yeah, sounds good. All right. So my principal is 1,000. My interest rate is 0.06. And I think we can all, right, you don't need to write 1 plus 0.06. You can just write, I know that's going to be 1.06. So okay. I can certainly try, yes. Zoom in a bit. How's that? Better? Okay. And then the teeth power, the number of years is going to be 10 years. You definitely are going to need to use a calculator for these problems. Like, this isn't something we're calculating by hand. So you should definitely, when you have these homework problems, you should get out your calculator. Or use a computer or your phone or whatever. 1,000 times 1.06 to the 10th power. 1.06 to the 10th is going to be about 1.79085. Really, I'm not actually going to write that down like I'm actually doing this as a problem on my homework. What I'm going to do is I'm going to do 1.06 to the 10th, and I'm going to multiply it by 1,000, and I'm going to write down that I'm getting that the amount of money is approximately $1,790.85. Okay. So let's see what happens if we calculate the interest. Question. Yeah.
Well, this is just a general question.
Yeah.
For our midterm, well, Well, first off, is the midterm in here?
No, so the midterm is going to be like the quizzes.
Okay.
It is going to be on your own.
My second question is that it says some calculator, but then.
Yeah, I'm gonna think about that a little bit. That's
do that?
generally how things have run. So if you had a question like this and you were told you could not use a calculator, this would be the answer you would it as.
What about like log 79 or something?
Exactly. Same.
So like if that's the question, you're like, okay.
Well, no, so I'm not gonna ask you questions. So I'm usually fairly thoughtful about the questions I ask, usually. And I'm not gonna ask you a question that would require a calculator answer if you're not allowed to use a calculator.
Okay.
So, yeah. Also, I very much recognize that I could say you can't use a calculator and some of you might still choose to. So I'm probably not gonna make that a requirement. I'm just gonna try and ask questions that don't really necessitate a calculator necessarily. So yeah, I need to think about when is our test? Is it this Friday? I'm like, is it this Friday or is it next Friday? Yeah. No, it's not this Friday. This is from last year. That's not the right schedule at all. It is right. Okay, that's what I thought.
Oh
So
my God. Which one is it? You all have to make it up.
we can look at it. So let's.
Are we gonna have a quiz and a midterm?
No, definitely not a quiz and a midterm. Look, just to be real sure. It's good to be on the same page. I should definitely put my current schedule on this, not this old one. That's dumb. So, just so everybody's on the same page. Let's see. Let's go look at the syllabus. Let's see. Yeah, we do have a midterm this weekend.
What?
Yes.
It could also be Saturday night.
Right, exactly, yeah. So on Friday, in 2 classes, we will do a review. So we have class today, then we have class on Wednesday where we'll talk about section next, which is I. And then on Friday, we'll have a review for the midterm, and then over the weekend, we will do the midterm. Yeah.
On this like syllabus thing, it says the midterms due Sunday.
Okay, sure. So the Sunday 5. And I mean, again, I'll point out, I'm not super stringent about the due dates. So I'll probably actually change it to like Sunday at 10. I don't want you starting too late. I personally don't like, and this may be my own bias. I don't find starting just late to be good. So I usually try to make it do like not at midnight or 2 in the morning, because that seems like a bad time to be finishing a test. So anyway, all right. So yes. Sure, right, exactly.
Did you get a haircut?
I did get a haircut. Thank you. Yeah, I was getting been a little too long since I had my last haircut. So let's talk about compounding the interest monthly, which would mean N was what? How many times are we doing it per year? Right. So N equals 12. And our formula is going to look like this. The amount is going to be the principal, 1,000, times 1 plus the interest rate, which is 0.06, divided by the number of times you're compounding it, to the 12th power times 10. What I really want to kind of point out here is what you're doing when you're compounding interest some number of times is you're taking the interest, 0.06, and you're dividing it by 12. And I'm just going to write down here, 0.06 divided by 12 is 0.005, or if you prefer, 0.5%. So what you're doing with that is you're taking your 6% of interest that you're going to earn over the year, and you're breaking up into 12 equal bits, each bit being 0.5%. And then each month, you're getting 0.5% of interest. So after 1 month, you're going to get 0.5% of interest on $1,000. 1% would be $10. Half of that would be $5. So after 1 month, you're going to have $1,005, the 1,000 principal and the 0.5% of interest you've earned. And then in the next month, it's going to compound because you're going to earn another 0.5% of interest. But now it's not on the original $1,000, it's on the $1,005, the original 1,000 plus the 5% interest. That's the compounding thing, right? Every month, instead of earning all 6% at the end of the year, every month you're earning 1/12 of that 6%, which is 0.5%. That's the whole idea there, really, is that you're just getting less interest broken up over more intervals. And let's see what happens when we do that. So that's going to be So 0.06 divided by 12 is 0.005. So it's 1,000 times 1.005. And 12 times 10 is 120. And then calculator time. This is going to be approximately $1,819.40. And what we see, and this is generally true, if everything else is the same, compounding something more frequently results in a larger amount. So we should pick the option to compound more frequently. So, oh, question. The question was answered. Great. So let's look at another example. So, as is typical with these kinds of questions in the ones last class, you're going to know some stuff and be asked to find something, right? You're going to know probably all the things but one piece and have to find the last piece. So suppose you invested $5,000 into a savings account. So I already know my principal is $5,000 and it pays 4% interest. So my interest rate is 0.04. Compounded weekly, which means n equals how many? 52 weeks a year. Yeah, not exactly 52 weeks a year, but close enough for math. How long will it take for your money to double? So they're telling us another piece of information there that's not in the exact words. We are asking how long until the amount we have is how much? Right. Double what we started with. And we're trying to find the time. Okay, well, we can throw this all into our compound interest formula so you guys can see that. So I'm just going to take this formula and substitute in all the known things. 10,000 equals 5,000 times 1 plus 0.04 divided by 52 to the 52 times t. Now, something to be aware of here. Well, actually, not quite yet. Let's do some calculating. So we're going to divide both sides by 5,000. And we're going to get 2 equal to, now this number here is a little bit sketchy. 1 plus 0.04 divided by 52 isn't going to be nice. It's not, it doesn't have a very finite decimal approximation, right? It kind of just goes on and on and on. So what I would say is you don't want to do any approximating until you're getting kind of to the end. So even though it's kind of terrible to write, I'm going to write this thing the whole way through until I'm actually using a calculator to calculate it. I'll show you what I mean. So I'm going to have this 1 plus 0.04 divided by 52 to the 52t power. And then I think I need to take the log of both sides. So I'm trying to solve for a variable that's in an exponent. And the only way we really have of getting that out is by taking the log of both sides. And you can use log base 10 or natural log or some other log. I'm going to use log base 10. I know it's a departure from my usual natural log choice, but felt like doing something different. So log base 10 of 2 equals log base 10 of all of this stuff. And the whole reason for doing that is to allow us to bring this exponent, 52t, down in front of the logarithm. That's the whole, right? When you see a variable in the exponent, you should automatically think, oh, I'm going to take the log of both sides, so then that the power can come down in front and not be in the exponent anymore. So then we're going to have log of 2 equal to 52t times log of this terrible number over here. And finally, I want to isolate t. So what am I dividing both sides by? Right, log of garbage, and also the, what else did you say? The 52, right? I only want the t over here, so I'm going to divide both sides by 52 times log of garbage. So we cancel the 52 there and 52 there and the log of trash and the log of trash. And we're left with t equal to log of 2 divided by 52 times log of 1 plus 0.04 over 52. And then is when I would get out the calculator. Like, okay, I would do 1 plus 0.04 over 52, and then I would do log of that, and then I would multiply by 52, and then I would do log of 2 divided by that answer, which is not great on a phone, right? On the phone calculator, that's going to be a lot of opportunities to make a mistake. I would definitely encourage you to use something better than the phone calculator. So this is approximately log of 2 divided by 52 times log of 1.00077. Now, again, here's the point I really want to make. This isn't the actual number, right? The 1.00077 is the number that I've chosen to write down. But the value you should actually use there when you're doing a calculator approximation is whatever that is with all of the decimals at the end that you can have, right? Use the value you get from the calculator, then take the log of that, then multiply by 52, then do log of 2 divided by that answer, so that you're not losing any accuracy by using a decimal approximation too soon. So try not to cut off your approximation until you absolutely have to. This ends up being approximately 17.32 years. How did I get 52? How many times how often were we compounding? Weekly, every week. And how many weeks are there in a year? There's 52. Yeah. So the number of times we're compounding is the number of things there are in a year. So if we're compounding, quarterly, that's every 3 months, because there's 4 quarters in a year. So there'd be 4 times we compound it.
I just had a question on something I was kind of confused before.
Sure.
On examples like this, when would you lose just a log and a natural log?
You could have definitely used natural log as well. This would have gone exactly the same way if you used natural log instead of log.
So it doesn't matter which one.
Doesn't matter at all. Yeah, you can use either one.
What's the difference?
Well, the difference is that the log base 10 is saying 10 to what power equals and stuff, and the log base e is saying e to what power equals and stuff. But when you're doing this sort of calculation, you end up getting the same result in the end. So it doesn't matter. Really, we're just the logarithm is a tool we're using to get that variable out of the exponent. And it doesn't make a difference which base we use. Yeah, good questions though. All right. Oh yeah. Now for something fun. So let's start with this. You can write down as little or as much of this as you want. It's more of an exercise to show you something about a particular number. Suppose I loaned you $1 whole for a year. What a nice guy I am. Well, not that nice. I charge you 100% interest. So, all right. How much would you owe me at the end of the year? Well, it depends on how often we compound. So if it was just simple interest, you'd owe me $2 at the end of the year, right? The principal plus the 100% of interest, the $1 plus another dollar, which is 100% interest. So that's kind of the process, the thought experiment we were doing here, I guess you could call it if you wanted to be funny about it. So using our compound interest formula, with the principal being $1, the interest rate being 1, right? Because 100% interest is a 1 as a decimal. And it's for 1 year, so times equal to 1. And then the end value, right? That's the number of times we're compounding. That's going to be the thing that we change to see what happens as we change it. So using those values, here's what our formula becomes. Our A equals P times 1 plus R over N to the NT power. Essentially everything except for N is 1. So P is 1, R is 1, and T is 1. And we're left with this formula here. So that's the amount of money you're going to owe me after 1 year, depending on how many times we compound it. So let's find the easy answer. How much money will you owe me if we only compound the interest annually? Well, we already said the answer, right? It's going to be $2, the $1 I lent you plus the $1 of interest. But let's see that the calculation actually works. So if n equals 1, the amount is going to be 1 plus 1 over 1 to the first power. 1 over 1 is 1, 1 plus 1 is 2, 2 to the first is $2. Great, I made $1. All right, the question gets more interesting if we change how often we compound it. So let's say we compound it semi-annually. And actually, I want to kind of talk about this calculation specifically, because I do feel like it helps you see how the compounding is really working. So we're going to throw it into the formula at the end. In fact, we'll do the amount's going to be 1 plus 1 over 2 squared. I prefer fractions usually. 1 is 2 over 2 plus 1 over 2 squared. That's going to be 3 over 2 squared, which is 9/4. Or 9 quarters, well, that's 8 quarters, which is $2 plus another quarter. I earned an extra 25 cents by compounding the interest semi-annually. Oh, sorry, can you see that? But I do want to point out here, this is a good example of how the compounding works. So if I compound it semi-annually, after 6 months, I'm going to get half of the 100% of interest. So after 6 months, well, I lent you $1. If the interest is 100%, but I'm only getting half of that, I'm going to get 50% interest after that 6 months. So after 6 months, I'm going to have $1 plus 50 cents, or $1.50. I got half of the interest. Okay, now in the next 6 months, I'm going to get the other 50% of the interest. So after the whole 12 months have gone by, I'm going to have that $1.50 plus 50% of interest on that amount, right? I'm compounding the interest. So I'm going to add 50% of $1.50, which is how much? 75 cents. And $1.50 plus 75 cents is exactly $2.25. So the formula really does work. Right? It's not just made up, it's actually working. But that's the idea, right? You're taking the amount of interest you're getting and you're dividing it into how many times you're compounding it. And then you're taking each fraction of that every so often. Now, we're not going to do that for each of these calculations because it gets a lot messier as n gets larger, but I wanted to point out that it really does work. So how much money will you owe me if we compound interest quarterly? Well, hopefully more. Let's find out. So the amount's going to be 1 plus 1/4 to the 4th. This one is where things probably get a little bit too big. You can do this as 5/4 to the 4th. But the numbers there, 5 to the 4th is 625. This is not really helpful information. 4 to the 4th is, I don't know. That's not true. I do know. It's 256. It's the only reason I know that is because it's 2 to the 8th, and I've memorized my powers of 2 because they come up a lot. And you've also played that stupid block game where you have 2, 4, 8, 16, etc. So I mean, come on. But this is approximately $2.61. So can I get infinite money from you if I charge interest more often? Well, let's ask a different question. Can I get $3 from you? Well, let's try. If we compound it weekly, I didn't even do monthly. I skipped monthly. It's fine. I've got monthly here. Oh, you know what? I made a mistake actually. This number here is not right. I apologize. That's the monthly amount. This is actually approximately $2.44. Sorry about that. The monthly amount is the $2.61. And if we do compute it weekly or compound it weekly, we get this number, which I'm not even going to do that. I'm just saying it's approximately $2.69. Right, getting closer to 3. Let's see if we compute it daily. You can see that. Well, it's going to be approximately $2.71. I'm gonna go a little further, 71 cents, 45 hundredths of a cent. It looks like it might be hitting a barrier, right? I will tell you, if you compute it minutely, every minute, you get $2.71.82 cents. And right, doing it every minute versus every day is not a big jump. So here's the idea. As n increases, this amount, 1 plus 1 over n to the nth power, gets closer and closer to the number e. So if I compounded interest continuously, which is the idea of, right, there's no interval of time between your next interval. If you compounded interest every moment of the day, I would get E dollars at the end of the year, or about $2.72-ish cents. But the real point of this isn't that I would get that much money. The point is that to know that when you take this expression, this 1 plus 1 over n to the n, and you let n get really, really, really large, this number gets closer and closer and closer to the number e. And that's actually how people usually define the number e, is that it's what this gets closer and closer to as n gets large. I do think it's worth seeing this graphically. So let me show you real quick. Here's what the graph of 1 plus 1 over n to the n looks like. And you can see, oh yeah, there's n equals 1, and you get $2 back. There's n equals 2, you get $2.25. And you can keep filling in values here if you really wanted to. I don't know, we can go big. But look at those values, right? They're just getting closer and closer and closer to E. You can plug in something, right? Oh, that's well, okay. I don't know about that. Desmos has some problems there. That was not correct. But right, if you get really, really big, the numbers get closer and closer. And you can even see that this graph has a horizontal asymptote at E. The values get closer and closer and closer and closer to E as the value of n gets larger and larger and larger. The reason I mention this is twofold. One, it's an important number. It comes up all the time. And its definition most likely will appear when you take calculus. Oh, you're not seeing, oh, that's right. Sorry, guys on Zoom. That's because I'm sharing the wrong thing with you. 1 second. I'm not sharing, I'm sharing the visualizer instead of the screen. There we go. That should work now. So one, it's an important number. You'll probably see this definition calculus. But two, it's also to get you kind of introduced to the idea of what's called a limit. So what's happening here is the limit as n is getting larger and larger of this function is e, because the function 1 plus 1 over n to the n is getting closer and closer to e. Don't sweat it too much if that sounds kind of weird. We're going to talk a lot more about limits in not this class. It's in the beginning of calculus. We don't talk about limits here. But that's kind of the idea. Yeah.
Is E also an infinite number or a non-infinite number like pi? Or
So when you say it, but what I think you want, what you mean is irrational. Yeah, it's definitely an irrational number. It has a non-repeating infinite decimal, like pi. Exactly. So when you think of E, you should definitely think of it in conjunction with the number pi, because they're very similar in that way. They're non-repeating decimals that never end. Just like the square root of 2 is also a non-repeating decimal that never ends. Yeah, that's a good point to make. All right, let me minimize this. Okay, so why do we mention that here? Well, because it comes up in the context of the continuously compounded interest formula. So if you're compounding interest continuously, then we get the amount of money via this formula. And really, the idea here is kind of what I was saying before. Well, it's not that important, actually. So maybe we'll say it if we have time at the end, but we might not have time. So again, this is your amount. There's your principal. There's your interest rate as a decimal, and there's t, the number of years. And there's nowhere to put n because n isn't a number, right? N is, I mean, you could say that n is infinite, right? You're compounding interest an infinite number of times, but there's nowhere to put infinity. You shouldn't be putting infinity in the formula. So if someone says interest is being compounded continuously, this is the formula you should think to use. And we often say the word PERT because it spells PERT, P-E-R-T. On the other hand, if someone says we're being compounded every, 12 times per year or whatever, then we have the, oh, n is equal to 12. You look like you had a question.
Yeah, so the continuously part, like, since interest is compounded at certain times, like, what is that continuously like?
So it means that you're literally compounding interest every, like, so it's compounded and then instantaneously it's compounded. You get like every moment of the day of the year, it's getting compounded. So every moment we're calculating a little bit more. It's not a great analogy. Here's what's
like
real.
a second, but it's like.
Right, exactly. It's every fraction of a second you could possibly compound it. And really where this is kind of coming from is if you take this compound interest formula, which is a times 1 plus r over n to the nt. And if you rewrite this as, I'm going to do some, you really don't need to write this down if you don't want to, because it's not super important, but you can rewrite this as 1 plus r over n to the n over r to the tth power. Sorry, to the r times t power. I didn't change anything, I just made it look different. N over r times t times r, the r's would cancel and you would get the nt power like we had here. The reason I'm writing like this is because this part here, this 1 plus r over n to the n over r, that's the thing that's going to get closer and closer and closer to the number e if n gets very, 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 very large. So the whole point here is that this becomes sorry, I used the wrong letters. I apologize. I got my A and my P in the wrong spots. That's terrible. That's not that terrible. I mean, I think you guys will forgive me. I can kind of fix it if I make things look awful. There, that's a P, right? Yeah, we all believe that. Okay. Sorry about that. So if we do that, then this becomes P times E to the RT. That's the whole idea there. Again, you don't need to worry so much about this. All we really want to take away from this is if it's compounded, so at every, I keep using the wrong word. If we compound it n times per year, we're going to use the compound interest formula where there's the n of it. But if we're compounding it continuously, we automatically jump to this formula here. And that's an important formula because it also comes up when we talk about exponential growth and decay. So let's look at some examples. Suppose you invested $100 into a savings account that compounds continuously. After 20 years, you have $500. What was the interest rate? Again, here's an example where we're just throwing things into a formula. I mean, I know it's kind of all there really is to do with these questions. So I'm just saying my formula is this. And I know that my principal is $100. My interest rate is what I'm being asked to find. And the time is 20 years. So, oh, and also the amount. The amount is $500. If I throw that all in there, I get 500 equal to 100 times e to the r times 20. What should I do next? Exactly. You're trying to solve for something in an exponent. You don't want that base to have a coefficient. So divide both sides by 100. And I usually rewrite r times 20 as 20r. Not necessary, but it's just pretty typical. 500 divided by, oops, I need to divide that side by 100 as well. 100s cancel. 500 over 100 is 5. E to the 20r. And now what should I do? Which base would be the best? Base E for sure, natural log, right? Because if one of the things has E as the base, then base E is the one we want. So you can either write log base E of 5 equal to log base E of E to the 20R, or if you want to be a lazy mathematician like everybody else, you can write natural log of 5 equal to the natural log of E to the 20R. Those are the same. Same equation. But if you're getting caught up with being like, I don't see the E when I write ln, then write log base E. It's really, really, really okay. I'm just doing this because years and years have driven it into me. And also because it's lesser. So now, what's the natural log of E to the 20R? 20R. And you can either do this in one step and just say, I know that the natural log of E to the something is just the something, or you can do it in 2 steps. You can bring the 20R down in front, and then you're left with the natural log of E. And then the natural log of E is just 1. Because you're saying E to what power equals E? Oh yeah, the power of 1. And then we solve for R by dividing by 20. So we get the natural log of 5 divided by 20. And then when you pull out the calculator, and that's going to be approximately, natural log of 5 is about 1.61 divided by 20. And so that's going to be about 0.08. So you can say that R is 0.08, or you can write it as a percentage and say that R is about 8%. Here's the interest rate.
Do you want us to write it as a decimal, or do you want us to write it as a percentage?
Either way would be fine.
Okay.
Just make sure you don't. So the only thing that would be not okay is if you wrote the rate as 0.08%, because that wouldn't be correct. You should either write it as 0.08, boom, or 8%. Some general strategy stuff. Identify which formula you need, right? If it's simple, it's A times 1 plus R to the T. If it's compound, it's A times, sorry, I keep saying A when I mean to say P. Apology. It's P times 1 plus R over N to the N T. And if it's compounding continuously, it's PE to the RT. Then identify what you know, figure out what you're trying to find, and then finally throw it all into the formula and then solve for the thing you're trying to figure out. And it's always going to be the most work to solve for like the rate or the time. Usually finding the amount, or I guess even the principal, if you're given everything else, are usually by comparison easier to find because they don't involve having to take a logarithm of the sets. Right. Couple more questions. Your goal is to have 2,000. Oh, here's a question where we don't know the principal. Your goal is to have $2,000 in 4 years. So we know the amount is $2 grand. We know the time period is 4 years. And the rate of interest is 10% or 0.1 compounded monthly. And that means N equals 12 times per year. All right, how much should we invest now? So again, put it all in the formula. So there it is. There's my P times 1 plus R over N to the N times T power, where my interest rate is 0.1, times the N is 12, the N is 12, and it's times 4. And just like I was saying kind of with the other problem is, I don't really want to simplify this or get a decimal approximation of this until the very end, right? 0.1 divided by 12 is not this. It doesn't, it's not a, it's a repeating decimal that's, I don't know, it's something not pretty. So let's go ahead and, well, actually, I mean, solving for P here is pretty easy. Easy, meaning it's one step. We're just going to divide by all of this. So P is going to equal 2,000 divided by, I can do a little bit of simplifying here in that I think it's 1 plus 0.1 over 12 to the 12 times 4 is 48 power. And now we get a calculator. So, okay, that's going to be, if you do 0.1 divided by 12, it's about 0.0083 forever. Not 83 forever, I mean 8333333 forever. To the 48th power. So you do this, this, raise it to the 48th power, and then you do 2000 divided by that, and you get about $1,342.89. That's how much principal or investment we have to start with, so that in 4 years, earning 10% interest compounded monthly, we would have $2,000. I don't feel like I'm showing you a whole lot here, really. I mean, I'm saying we've got these numbers, we put them in a formula, and then we use tools, right? Because there's no, I mean, no one's calculating this by hand. Unless you have all the time in the world. Yeah.
You're not too strict on error, right? Like when it comes
Yeah,
to
like if you had like 88 cents or even if you rounded to the nearest dollar.
Yeah, because on the calculator it gave me like 86. So I was like, oh.
Right. I might have rounded it wrong. So what I will point out though is the reason you might have gotten a slightly different answer, and I don't know what you did exactly, is you might have approximated this.
And I plugged in the
You
top
did
one
that?
exactly.
Okay. So maybe I did something different. Yeah, as long as it's close. I will also mention just in general, that if you're not asked for a decimal approximation, typically you should give an exact answer. Now that's not true. Like these questions, these like how much money should there be at the end of the year or whatever, these ones you should always give an approximation for, right? If it's a homework problem and you're like, how much money, I don't want to see this as your final answer because it's not super informative. I'm like, well, I don't know how much that is. So for these kinds of problems, you definitely should get out your calculator and get an approximate value. But for other things, like when you're just asked what's the solution to this equation, and the answer is like, 5√2, that's the answer we want. We don't want the decimal approximation unless specifically asked. Okay, one more question. You have $1,000. You want to grow it to $2,000 in 4 years. What interest rate do you need if interest is compounded continuously? All right, let's write down all the things. The principal is 1,000. The amount we want to have is 2,000. The time frame is again 4 years. We don't need to talk about how many times it's compounded because it's compounded continuously. And there's not going to be an end value showing up in the continuously compounded formula. That's actually another good way to know which formula to use. If they're saying compounded continuously and you accidentally start using, right, the compound interest formula, when you start asking yourself, well, what's n? I don't see how many times you're compounding it per year. Oh, well, I mean, I do, it's compounded continuously. That means we don't have an n value. N is getting infinitely large. So we're like, oh, that's not the right formula. We want the compounded continuously formula. For 2-in-1 shampoo and conditioner. They still make it, right? I'm sure that's still in the stores. But yeah, I mean, yeah, it is. That's what I was thinking when I see perk. It's 2-in-1 shampoo and conditioner. Yeah, I know, right? So that's what we're doing. We're trying to find the interest rate we need to double our money in 4 years. So let's put it all into the formula. We've got 2,000 equal to 1,000 times e to the r times our t value, which is 4. And we're just going to solve this in the usual way. Divide both sides by that coefficient. 2,000 divided by 1,000 equals e to the 4r. That's 2 on the left. I probably should have just simplified it that way. And then we're going to take the natural log of both sides. The natural log of 2 equals the natural log of e to the 4r. And I do want you all to get comfortable with telling yourself when you take the natural log of e to the something, you just get the something. Because it's going to happen a lot. So you want to get very comfortable with going straight from this step here to just saying, oh, that right side is 4r. The natural log of e to a power is just the power. And then on the left side, we have the natural log of 2. I'm not going to get the decimal approximation there, which is about, 0.7, I think. And then divide both sides by 4. So r is the natural log of 2 divided by 4. And then I would use a calculator and say, okay, r is approximately, natural log of 2 is approximately 0.69. And 0.69. And really, I mean, I wouldn't actually do this calculation. What I would actually do is just do natural log of 2 divided by 4 on my calculator and see what I got. I'm going to get approximately 0.173. So my answer could be that, or you could say it's 17.3%. Either answer is totally acceptable.